Hello everyone, welcome to the second tutorial of Signals and Systems. In this tutorial, we have questions related to LTI systems and convolution. So the first question says that there are three systems H, G and F, each of which are defined in this way. And Xn is the input to each system and Yn is expressed as a function of Xn. And that is the output. Yn is the output of each system. Then it says that in figures 1.2 to 1.7, there are different combinations of these H, G, and F shown, right? And it says by expressing the output Yn in terms of input Xn, determine which of these systems are equivalent. Now, parallel you already understand, and cascade basically means series. So to start with, what we'll do is for each of these, we will write the output Yn in terms of Xn. We already know from above what each of these H, G, and F, what do each of these functions actually do. So if X is the input, H gives us square of that input, right? So this would have been X square N if this was the input, and G gives us Xn minus Xn minus 1. Okay, and we can clearly see that output Y is nothing but this term plus this term. Okay, so I'm going to write it separately, maybe below. All right. Part B, we notice that G and H are added together. So we know that output of Y will be simply output of whatever is the output of G plus whatever is the output of H. So we can clearly see that it doesn't matter whether this was placed up or this block was placed up down like it is placed in part 1, because addition is commutative. You can say that part B output is also the same, right? Plus X square N. Now in part C, we have X as the input to G. So if X is the input to G, what would be the output of G? Xn minus Xn minus 1. Okay, Xn minus Xn minus 1. And now when this is the new input to a function H, which simply does square of this, so you would get Xn minus Xn minus 1, the whole square. This is what is going to be the output. So let me write it. Yn is Xn minus Xn minus 1, the whole square. You can also open it up and write it as, going to part D, H is added first now. These are two blocks again in series or cascade. H is added first. So if Xn was the input, the output here would have been X square N. And now we have a block G. This is the output Y, right? So here what we will need to do, this should be X square N minus X square N minus 1, right? Because that is what G does. Okay, moving to part E, we notice that G and F are connected in cascade. What does system G do? Taking input as Xn, it computes Xn minus Xn minus 1 as its output. Now when this is fed as an input to system F, what does the system F do? So let me just quickly rewrite here what F actually does so that we don't have to go on scrolling again. System F, if it takes an input Xn, it gives an output 2Xn plus Xn minus 1, right? This is what section F does. 2Xn plus Xn minus 1, right? So now that we know what is the input, we can say that Yn in that case would have to be 2 times the input. So 2 times the input, which is Xn minus xn minus 1 plus the input shifted by 1 unit. That means the first term shifted by 1 unit minus the second term shifted by 1 unit. So xn minus 1 becomes xn minus 2. Let us open this bracket. So you've got 2xn minus 2xn minus 1 plus xn minus 1. That would give us minus xn minus 1 minus xn minus 2. Okay, moving to part F, we notice that it's again a cascade combination, but block F is connected first and then G is connected. So if xn was the input, the output of block F, as we know already, would be 2xn plus xn minus 1. And now this is the new input to block G. For all the other questions also, you could have just assumed like this to be another new signal alpha n, and that you consider that as the input to block G, right? And what does block G do? Block G simply takes the input and its time shifted version by 1 unit and then finds the difference of the two. Okay, so in that case, what would be the output yn? The original input, so 2xn plus xn minus 1, original input, minus time shifting by 1, so 2xn minus 1 plus xn minus 2. We open this up, so we would get 2xn plus xn minus 1 minus 2xn minus 1. That means minus xn minus 1. And when you open the bracket, this also becomes minus xn minus 2. Right? So by looking at it, we also notice that these two are equivalent. That means section E and F are equivalent systems. We also notice from the beginning that section A and B, these two systems are also equivalent. Okay, because firstly, in parallel combination, it doesn't matter in which order you connect them. That's why they are equivalent. And in series, it doesn't matter which one you connect first and which one you connect later. You will still get the same output, because you must have studied in convolution that actually the output is a convolution of input and the system's impulse function. Right? So it doesn't matter which one you connect first and which one you connect later. Eventually, you have to do a convolution of all these system responses, system impulse responses, and the input. And convolution is a commutative operation, and which is why it doesn't matter which one you place first. Moving on to question number 2. Consider an LTI system whose response to signal xt in figure 2.1a is the signal y1t, which means we've got some system. It's a continuous time system, right? So let its impulse response be ht. What is given in the question is that if x1t is the input to this system, the output is y1t. This is what is x1t and this is what is y1t. Okay. It is also very important to note that the question says that it is an LTI system. Okay. Why this is important, we'll see shortly. The question asks us to determine and sketch carefully the response of the system to input x2t. That means, see, what is xt, what is ht, we do not know, but we know that this is a system where if you give x1t as the input, that means where you give this as the input, you get this as the output. This is one thing we know. And the other very important thing to know is that this is an LTI system. That means it's a linear time invariant system. The beauty of it being a linear time invariant system is that because it is linear, if you multiply an input by a certain factor, it means that the output would also be multiplied with that factor, right? And it being time invariant means that if you know for a certain input what is the output, you can say with guarantee, since it's a time invariant system, that if the input was shifted by an amount capital T, then the output will also be shifted by that same interval, that same duration. Okay, this is possible only because this was a time invariant system, and also some if xt gives an output yt, if you multiplied it with a factor alpha, say, output would also have been multiplied with a factor alpha, right? If you had multiple terms individually adding, being weighted with different weights, the output will still be same. That means if x1t gives y1t and some x2t gives y2t, a system being linear means that alpha times x1t plus some other beta times x2t, if this is the input, it would still give alpha times y1t plus beta times y2t. So this is what linearity and time invariance guarantees for us. How this is important is because in this question, we do not know what is HT. If we know HT, right, if we know the impulse response and then somebody gives us an input, we know very easily how to find the output. The output is simply a convolution between XT and HT, right? But we do not know HT here. We only know that the system is LTI. So how do we proceed? Okay. If in such a case, what you would do is that because you know the system is LTI, you try and write this second signal for whom you need to find output. You try and find how you can write this signal in terms of the signal which you already know. Okay, so if I look at x2t, x2t looks like x1t as it is, right? This is x1t, and this part is what? This part is what you get when you shift x1t by 2 units and then multiply it with 1. That means this signal in red would be what? x1t minus 2. And if I was to multiply this with minus 1, this would mean minus x1t minus 2. Right? That means x2t can now be written as this should be simple brackets. We use square brackets only to represent discrete time signals and simple brackets to represent continuous time signals. So x2t can be written as x1t minus x1t minus 2. Because you know that the system is an LTI system, and if x1t gives y1t, then x1t minus x1t minus 2 in this system should result in what? It should result in y1t minus y1t minus 2. Correct? And then how would that signal look like? That signal would look like y1t, which is y1t, all right. Then y1t shifted by 2 units. y1t shifted by 2 units looks like this. This is y1t minus 2. And now when you reflect it, that means you multiply it with minus 1, this would look like this. So this part of the signal is minus y1t minus 2. So remember what the question asks. Always please remember to read the question carefully. Determine and sketch carefully. So determination you've already done. This is what is the output, right? Output of the system as a response to signal x2t. This was x2t. It also asks you to sketch it. That means you would say this is the system, and to this system, if x 2t was the input, the output would be y2t. Okay, and what is y2t? You just found y2t would be y1t minus y1t minus 2. This is how this is the determined value, and to sketch the signal you would make y2t like this, right? This is 2 units, this is 4 units. So this is y2t, the response of the system when input is x2t. Part B says, determine and sketch the response of the system considered in part A to the input x3t. Now what is x3t? This is x3t. Okay, so again, because in this question we do not know what is HT, the impulse response of the system, we only know input, one set of input and output, and we know that this is LTI system. So now let us try to write x3t as a function of x1t. Only then we will be able to find the output y3t. Okay, if you look at x3t, this looks like if x1t was maybe shifted by 1 unit, right, to the left side, and then added to x1t, what would you get? You would get something like this. From -1 to 0, the signal would have been like this. From 0 to 1, you have two values of 1, so you would have got something like this, right? And from 1 to 2 again, the signal is just 1. So this is what you would have gotten. Right? That means x3t is nothing but x1t plus x1 shifted this side by 1 unit. That means x1t plus 1. Now because x3t can be written as x1t plus x1t plus 1, that means what would be the output? In other words, we are saying if x1 resulted in y1t, which is given, what would x1t plus x1t plus 1 result in? That is what we are asking. So because this is an LTI system, obviously it would give you y1t plus y1t plus 1, right? So let's write that. Now you're also asked to sketch this signal. So how would y1t plus 1 look like? If this is y1, y1t plus 1 means this whole signal shifted to the left side by 1 unit. This is how y1t minus 1 would look like. Sorry, y1t plus 1 would look like. And now you've got to add these two signals, right? So adding these two, how would that work out? This is minus 1, right? So before minus 1, the signal is 0. -1 to 0, there is nothing but this signal. From 0 to 1, you notice that there are two signals to be added, and at the extremities your value is 2. Here it will be 2 plus 0, and here it will be again 2 plus 0, right? So extremities are done, right? And what do you notice? What do you think should happen in between? These are two straight lines, so when you add, it is basically always going to result in the value 2. That means it's a straight line. What happens between 1 and 2? Again, only this signal is there and everything is 0 afterwards. Okay. So this signal in red, this is actually y3t, which is nothing but y1t plus y1t plus 1. Moving on to part C. Part C says, suppose that a particular discrete time linear but possibly not time invariant system has responses y1n, y2n and y3n for the inputs x1n, x2n and x3n respectively. That means again there is a system. We do not know what is its impulse response, but we know that if you give different inputs like x1n, x2n and so on, it results in these outputs. So x1n gives y1n, x2n gives y2n and so on, right? Another very important thing here is that it says that it is linear, right? That means you can always multiply the input with some factor and claim that the output would also be multiplied with the same factor. But because it says that possibly not time invariant, you cannot use that logic that if input was shifted by an amount capital N, output may not be shifted by the same amount, because it says that possibly not time invariant. So this property we cannot use. Okay, only multiplying with a factor and assuming that output would be also multiplied with the same factor, only that's what we can use, and maybe addition. Okay, so knowing this, the question says that if the input to the system is xn, and what is xn? This is xn. Then what is the output yn? So just the same approach that we used in the previous case, but instead of trying to represent xn in terms of time shifted or scaled version of x1, x2, we will simply try to write them as a summation, as a weighted summation. Okay, so as you can see, how can xn be represented? Xn can very simply be represented as this element is coming from x1n, right? Because x1n did not have any other elements. The element at -1 would have been coming from x3t, maybe you can say this is twice of x3n, right? Now the one at n equal to 1. Okay, so the only way to do that is to write in terms of x2n, but x2n also has a value at n equal to 0. So let me just do a hidden trial and try to write the function. So what if I wrote a signal? What if I try to write xn as 2x1n minus 2x2n plus 2x3n? Do you think it's going to work? It's like saying on the same time scale, if I try to draw, 2x1n would mean this, minus 2x2n, meaning this, plus 2x3n means, okay, so if I add them all up, I'll notice that here at n equal to 0, I'm going to get a 0, right? But I need a 1. That means I need not 2x1n but 3x1n. So this should have been 3x1n. This is going to give me x1n, right? At -1, I'll get a sample of value 2. At n equal to 0, I'm going to get 3 minus 2, which is equal to 1. And at n equal to 1, I'm going to get a -2. All right. So this is how I can write xn, and because this is a linear system where if x1n results in y1n, then this function of x1n should result in what? An output yn, which should be equal to 3 times y1n minus 2 y2n plus 2 y3n. Right? So this is what is the output. Now moving to the next part. if an LTI system had a response y1n to input x1n, what would be its response to x2n and x3n? Okay, so now in the part D, it is clearly saying that it is linear and it is also time invariant. That means now we can try and express the signal xnt in terms of a shifted version, okay, in terms of shifted version of x1 and x2. Okay, so now it is saying that what would be the output if now this is the input, right? So y1n is what you know, right? Because we need to write it in terms of y1n. That is what is given. If LTI system had the response y1n to x1n, so now you need to write it in terms of y1n. So how do I express x2n now? I can say x2n is simply x1n, right? And then shift it by 1 unit to the right and add them up. So this is what is x2n, and because it is an LTI system now, I can always say that if x1n gave a signal y1n over an LTI system, then x1n plus x1n minus 1 should give y1n plus y1n minus 1. Okay, and this is what is x2n, and this is what is y2n. Okay, so this is what you'll get for x2. Similarly, let us try for x3. How do we write x3 in terms of x1n? X3 is simply, you can notice that x1n moved to the left by 1 position. This is nothing but x of n plus 1. That means that if x3n is nothing but x1n plus 1, this is going to give an output y1n plus 1. Understand that here it said LTI, that is why we were able to write like this. In the previous case, it did not say that it is time invariant. That is why we were trying to represent it in terms of scaled versions of x2 and x3. Moving on to next question. Determine whether each of these following systems is linear and or time invariant. In each case, xn denotes an input and yn is the output. Assume x0 is greater than 0. Like I said, if x1n gives y1n and x2n gives y2n in any system, then alpha times x1n plus some constant beta times x2n. If this was the input, it should have given the output alpha y1n plus beta y2n. Let's just check this. So let us say we have an input for this system. We have an input x1n that gives an output y1n, which is equal to x1n in this case minus x1n minus 1. Okay, that is what this system does. Let there be another signal x2, which results in an output y2n, which is x2n minus x2n minus 1. Let us now define a new signal x3n, which is equal to alpha times x1n plus beta times x2n, and let us see what this would give us if this was fed into such a system where output is xn plus xn minus 1. So basically what this does is takes the input, keep it as it is, plus shift it by 1 unit and add it, right? So let us just keep everything as it is. Okay, so now let's open this up. What is this? Alpha. Can I write this as alpha? These two terms together. Alpha x1n plus x1n minus 1. Yes. Plus beta times x2n plus x2n minus 1, which is nothing but alpha times y1n. Right? This is what was y1n plus beta times y2n. Since we have proven this, it is safe to say that this system is linear. Now testing for time invariance. What do you need to prove? You need to prove that if some signal xn results in a output yn, then if the input is shifted by an amount capital N, this would mean that the output is also shifted by capital N. So let us try and do that for part A. So let there be a signal x1n given as the input to this system, which gives an output y1n, which is simply x1n plus x1n minus 1. This is known. Okay. Now let us shift this signal by an amount capital N. Let me call that a new signal x2n, and this is x1n minus capital N. Okay. So when x2n is fed in, what should be equal to y2n? Y2n should be x2n x1n minus 1, right? So what is x2n? x1n minus capital N. And what is x1n minus 1? This would be this should be x2. Right? So what is x2n minus 1? x2n minus 1 would be x1 n minus 1, right? Which is same as saying, since y1n was this is same as saying that this is y1n minus n. Because if you plugged in, instead of n, you plugged in n minus n everywhere in y1n, this is what you would have got, right? Because y1n is this. So if I had asked you to find yn minus n, what would you have written? x1n minus n, x1 n minus capital N minus 1, right? Which is same as this. This shows us that the system is also time invariant. Okay, we move on to part B now, where now there's a different relationship between input and output. Okay, so it's the same as previous part, but there is an additional x0. Notice that this term x0 is not a function of n. It's not a function of time, like sample value. Not time, here it should be called in terms of sample number, but it's not a function of sample number. It's a constant. And if you notice earlier in the question, it says that assume that x0 is positive. That means this is a positive number. It is given. Okay, so let's do the same thing. Let's show it for linearity. Now for linearity, it's pretty simple. So I think you can do that yourself and you would be able to show that the system is linear. But in terms of time variance, if let us say we defined a new signal x, so x1n results in x1n plus x1n minus 1 plus x10, and let me define a new signal x2n, which is x1n shifted by an amount capital N. So what would you get if you fed in xn minus n? You would get x1n minus n plus x1 n minus n minus 1 plus x0, right? But at the same time, if you try to write y of n minus n, like y1 of n minus n, what would that be? Replace n with n minus n everywhere. You would have got x n minus n plus x n minus n minus 1 plus this also needs to be shifted, right? So this would have become 0 minus n, which is not equal to the output of the system that you would have gotten for. So these two are not equal. Okay, so it is not time invariant. Now let us look at linearity for that matter. Linearity is pretty simple to explain. So let x1 give you an output y1, x2 give you an output y2n. And what are those outputs? x1n plus x1n minus 1 plus x10 and x2n plus x2n minus 1 plus x20. Now let me define a new input x3n, which is alpha times x1n plus beta times x2n. Let this give an output y3n, and what would y3n be? Y3n would be x3n plus x3n minus 1 plus x30, which is, let me write it here, y3n would be what? x3n, that means alpha times x1n plus beta times x2n, this term, plus x3n minus 1, so alpha times x1n minus 1 plus beta times x2n minus 1 plus x30. And what is x30? X30 would be nothing but alpha times x10 plus beta times x20. Now let me open the bracket. Let me take all alphas together. So it becomes x1n plus x1n minus 1 plus x0 plus beta times x1n, x2n, sorry, plus x2n minus 1 plus x20, which is nothing but alpha times y1n plus beta times y2n, which is why the system is linear. So this system is linear but not time invariant. Or the system is time variant. We move on to the next question, question 4, which asks us to determine discrete time convolution of xn and hn. Xn and hn are given here. So you already know that in order to find convolution is nothing but it's a shifted, reflected, weighted summation, right? So you can write it as x k h of n minus k varying from minus infinity to plus infinity, and this is also same as writing x of n minus k into h of k summed up from minus infinity to plus infinity. So you can choose any one of these two signals and decide to flip it and then shift it by each unit, and for each shifting you find the product of that shifted version with the other signal and you add them all up, right? So it's always easier and preferable to shift and reflect the very simple the simpler of the two functions. So I'm going to choose to flip and reflect xn. So the first step you do here is first convert everything to k axis, because you've got to multiply xn minus k and hk. So let's change the variable and make it k. And if this is xk, which is at 2, right, everything else is 0, then what would be x of minus k? X of minus k would be this xk reflected about this axis. That means this is how x of minus k looks like. And if this is how x of minus k looks like, how does x of n minus k look like? So we follow the same principle as before, where we talked about compound scaling and shifting, right? And there, because you are now doing x of n minus k, you will be moving, you are basically moving. When I ask you to do x of n minus k, what are you doing? You are basically doing x of minus k minus n, right? So this scaling you have already done before. So this time you will have to shift it by minus n to this side, to right side. You're basically doing it, you're doing a translation by minus n on the scaled version, right? So if this is x of minus k, how would x of n minus k look like? In general, you would say x of n minus k would look something like this, where what is this point? This is like saying x of 0 minus k, right? So at n equal to 0, your signal is at minus 2. So what would be x of n minus k be like? It will be x of n minus 2. So just think of this to be one special case of n equal to 0. So if n equal to 0, then this becomes k equal to minus 2, which is this case, right? X of minus k. So the first task in doing any type of convolution is to obtain the first signal, and we have obtained it. We've got x of n minus k. And the second signal, we are going to do nothing with it. I'm just changing its variable to k. Okay, and call it hk. So now we've got both the signals that we need. And now we are going to find a product of these two signals and sum it up for all values of k. Right? Now, for all values of k means from minus infinity to plus infinity for the entire number line. Okay, but remember that this is going to be a signal which is a function of n. Right? So it is very important to know where this n minus 2 is to find the product. Right? So I'm going to use this signal, and let us say this is where your x of n minus k is situated. Okay, that means n minus 2 has not, this signal has not yet reached here. That means the case I'm talking about is for n minus 2 less than minus 1, or in other words, n is less than 1. Okay. In that case, what happens? We know that there is no overlap between the two. That means by n, this product is going to be 0. Next, let us assume this has moved forward, and now xn has reached somewhere here. Okay, or it is here, or it is here. That means it can be anywhere between 0 and 4. In other words, I want to say if n minus 2 is between 0 and 4. See, another important thing here is that because these are discrete time signals, right? So it's better to use less than equal to. So here I should have actually said n minus 2 less than equal to minus 1. right? Because even if this n minus 2 was situated here, there was no overlap between the two. So n less than 1. Okay. And now I say if n minus 2 is less than equal to 0 or less than equal to 4. In other words, n is between what and what? N is between 2 and 6. If this is the case, right? So yn would be what? For each of these individual values, you basically need to multiply this xn minus k with your signal, right? So it's actually not a great idea to write it in a range because it's individual for individual value. So I'm going to write it as, so this is fine for all values less than 1, yn was 0. But when, we'll have to take each value one at a time. So we will need to find y2, y3, y4, y5, and y6, right? Let's see what are each of these values. So when n is equal to 2, xn minus k is here. Rather here, its value is half, right? So what would be y2? xn minus k, which is half, multiplied with this whole signal. But you notice everywhere else xn minus k is 0, xn minus 2 rather is 0. So this is just half into 1, half. You will get y3 when n minus 2 is equal to 1. That means this is here. What do you get when you find the product? You get half into 2, that is 1. Now it has moved here. N minus 2 equal to 2 means n is equal to 4. At n equal to 4, you have half into 3, so 3 by 2. And by 5 is what you will get when this comes here. That means basically you're saying that this is n minus 2, right? So when you find a product, what is this? 2. You again get a 1. And y6 would be half. Okay. Now what happens when it has reached here? Again, there is, right? That means this is n minus 2. Again, there is no overlap between the two, so the product will be 0. That means if for n minus 2 greater than equal to 5 means n yn is again 0. So all you have is non-zero samples between 2 to 6. 0, 1, 2, 3, 4, 5, 6. So yn is 0 for everything between before 1. So these are all zeros. For n equal to 2, output is half. For n equal to 3, output is 1. For n equal to 4, it is 3 by 2. For 5, it's again 1. For 6, it's again half. 7 onwards, it's again 0. So this is how yn looks like. There's a shortcut to compute this signal if we had simply used the shortcut of convolution here. And if we could write this xn as sequence of numbers 0, 0, half, 0, right? And state that this is the origin. And we could have written this this hn as sequence of numbers 1, 2, 3, 2, 1, and state that the origin is here. Okay, so wherever is the origin, the sample corresponding to the origin could be written like this. And if we took both these down and used a shortcut, let us cross check if we would have gotten the same thing. Okay, so I write this sequence here. So 0, 0, half, 0. Why I took the 0 is because I need the location of the origin. Okay, so I needed to take it till the origin. And the other one is 1, 2, 3, 2, 1. Okay, now I'm going to write the product of each of these. These are all zeros. The product of each of these with this particular row. I'm sorry, did not mark the origin here. This is the origin, okay, for the second signal. So I've written HN here and XN here. Now find the product of each of these numbers. So these two rows are all zeros because these two were 0. This would be half, 1, 3 by 2, 1 half. This would again be all zeros, right? Now the next step to do here in this shortcut method is to take all these diagonals, add them up, and the one diagonal corresponding to the intersection of both the origins, that in our case is this one, this is where your origin will be. Okay, so now how do I write the output using this shortcut method? I can say add each of these diagonals. So the first diagonal is just 0. Next sample is 0 plus 0. Next sample is half plus 0 plus 0, half. Next is 0 plus 1 plus 0 plus 0, 1. Next is addition of all these. That is again 3 by 2. Next is you add these 3, 0 plus 1 plus 0, 1. Next is you add this, half, 0, right? And now where is the origin? Where the two origins actually intersected, that is here, the first one in our case. Okay, so let us see if this actually matches with what you got in the previous case. Remember what each of these sequences means. So origin being here means this is n equal to 0, this is n equal to 1, this is n equal to 2, n equal to 3, n equal to 4, n equal to 5, n equal to 6, n equal to 7, right? So n0 is 0, correct? n1 is 0, correct? n2 is half, right? n3 is 1, n4 is 3 by 2, n5 is 1, n6 is half, n7 is 0, and everything above that is also 0, right? So you notice you get the same answer using the two methods. So if this kind of a question comes in a competitive exam, which is time bound like GATE, right? So this shortcut method will help you save a lot of time. Moving to question 5. Determine the continuous time convolution of xt and ht for the following three cases. So this is the first case we pick up. Now xt and ht both are same. So there is not much choice here to choose a simpler signal to reflect and shift. So I'm just going to take xt. So what is the first step? What are we trying to find? We are trying to find the convolution xt with ht. We know that convolution is defined in continuous time. It is x of tau, h of t minus tau d tau, tau varying from minus infinity to plus infinity, and it is also same as if instead x was reflected and shifted and h remained as it is, d tau. Convolution is commutative in this way. So the first step now would be to first write both these signals in tau domain. So this is x tau. If this is x tau, I'm choosing x to reflect and shift. So if this is x tau, this is x of minus tau. And if this is x of minus tau, then in general, t minus tau you would have had x of, instead of just minus 4, you would have t minus 4. Okay, so I'll just redraw this. What we said was that x of t minus tau looks something like this. Here you've got t minus 4, and if this is t minus 4, this would be what? T. And x tau is somewhere here. There's no overlap between the two. That means we are basically saying that t is less than 0. That means this edge and this edge have not yet met each other, right? So t is less than 0. In this case, yt, which is the convolution. So you had to find the product first, right? So this is 0. Let's look at the next case where this has moved further, something like this. So this is t and this is t minus 4. What is this value? I think it's 1. Now, if we were to multiply these two signals, let me draw this signal in blue. So if you were to multiply the two, the only overlapping region is this, right? That means 0 to t is the only common area. So if we were to write this convolution yt, right, means minus infinity to infinity x of t minus tau h tau d tau. If this is what we are writing, now the limits would be simply 0 to t. What is x t minus tau? This one. What is its value? 1. What is h tau in this region? 1. So this means 0 to t tau, that means plug in the value, it is just t. Okay, and what is this range? We are saying that this particular edge, that is t, it is greater than 0, okay, but it is still less than 4. Means it has not crossed this particular edge. This edge, this leading edge, has still not crossed tau equal to 4. Okay, so this is the output for this case, for t between 0 and 4. Okay. We move on to the next case. Now, h tau is still standing where it was standing. But x of t minus tau has become something like this. Right? So this is t minus 4. In this case, what is the condition first? This condition corresponds to for t greater than 4, but t minus 4 is still less than 4, right? Means this trailing edge, this is still inside. So we can say t is greater than 4, but t minus 4 is still less than 4. Means t is still less than 8. So t is between 4 and 8. In such a case, that is this particular case, how do you write yt? Now when you have to plug in the limits, you know that this is the only common area of overlap. There's no point in multiplying anything outside this. So what are these limits now? T minus 4 to 4, right? 1 into 1 d tau, which is simply tau putting limits from 4 to t minus 4. This would give you what? 4 minus t minus 4, which is equal to 4 minus t plus 4, 8 minus t. The fourth case, now let us assume that everything is the same. This is still h tau, but this time your x of t minus tau has actually crossed h tau completely. That means this t minus 4 has crossed 4. So the condition we are looking for is that t minus 4 is greater than 4. That means t is greater than 8. In such a case, we can see that there is no overlap and this yt is going to come out to be 0. Okay, so it's always very important that for questions of convolution, you summarize your solution, okay, properly. So let us write it in one place. Let us write it here. What is yt for different cases? Okay, so for t, what did we see first? For t less than 0, yt is equal to 0. Next case was for t between 0 and 4, yt was t. Next was for t between 4 and 8, yt came out to be 8 minus t. And then for t greater than 8, yt came out to be 0. Right? So, this is how you need to summarize your final answer. If I had asked you to sketch this, how would it look like? For t less than 0, signal is 0. For t between 0 and 4, the signal is a straight line having slope 1. Alright. For between 4 and 8, it is a straight line having a slope minus 1. Right. And above 8, it's again 0. What would be this value? This would be 4. Okay. So this is how yt would be sketched as. Alright. So you take each case. Also remember to write the range and then find the output. Okay, and then summarize it. Remember to summarize it. So we move on to part B. Now, obviously between these two signals, I'm going to choose HT this time to flip and shift. So the first step is to write the signals in tau domain. Solving questions graphically is always an easier way, but it's important that while writing the extremities of the flipped version, you do not make a mistake, because that is the only point where you can make a mistake. If you write that correctly, the probability of you making an error in a convolution question almost reduces to 0. Okay. So now my challenge is to find h of t minus tau. This is what I want. So first I'll write h of tau. H of tau is this. H of minus tau, this is h of tau. If this is h of tau, h of minus tau is this. This is h of minus tau. If this is h of minus tau, meaning corresponding to t equal to 0, how would h of t minus tau look like? Something like this. So if you plugged in t equal to 0, this would have been 1, and that is what h of minus tau look like. Right? So now this axis and everything means nothing, and I've got, there's only one extremity, it is t minus 1. So I've got my ht minus tau and its value is 1. This is the limit. Now all I have to do is just keep scanning it over this x tau and find the product and integration. Okay. So the first case is this value is 1, right? So the first case is when, say, case like this. So the case is that for t plus 1 less than 1, that means t less than 0. Until these two edges have not met, the product is 0. Moving forward, this edge has moved further, and let us say now this is the situation. Okay. The one in blue is ht minus tau. Now if I ask you to find the product of ht minus tau and x tau, the condition is that for t plus 1 greater than 1, that means t greater than 0. Now what is yt? Yt is integration from minus infinity to plus infinity, but obviously this is the only common area of overlap between 1 to t plus 1. That means the limits are 1 to t plus 1. And what are the two signals being multiplied? X tau, and x tau is what? E to the power minus tau minus 1. Ut minus 1 I can ignore, right, because its value is 1 only in this interval, multiplied by ht minus tau, whose value is 1, d tau. So how do you integrate this? You can always use substitution of variables. So say let tau dash be equal to tau minus 1. So d tau dash be d tau, right? And now let the limits remain the same, and now you can say that this is equal to minus tau dash d tau. And what is this? E to the power minus tau dash divided by minus 1. So there's a minus 1 between 1 and t plus 1, and now you replace tau dash with tau, which is this. So now when you are plugging in the value, you are basically saying minus e to the power minus t plus 1 minus 1 minus e to the power 1 minus 1, which is 0. So this is 1. So this is like saying 1 minus e to the power minus t, right? So the output is pretty simple. Yt, which is the convolution, is 0 for t less than 0, and it is 1 minus e to the power t for t greater than 0. So this is the answer, which you should summarize at the end. You can sketch this on your own. Moving to part C, this is very interesting because here we have to find a convolution between a regular signal and a delta function. Now you already know how a delta function is defined as. Delta function is 0 for t not equal to 0, and it is infinity at t equal to 0. Infinity or undefined you can say, but a very important property. This is not the complete definition of delta t. The definition of delta t is complete only when you state clearly that from minus infinity to plus infinity, the area under this delta function should be equal to 1, right? That means this is it can have different approximations, triangular or rectangular or whatever, but what this says is that this into this infinitesimally small width, this area is equal to 1, right? So if the width is tending to 0, the height is going to tend to infinity, and we represent a delta function not in terms of its amplitude, but in terms of its strength. That means the area under its curve. Okay? We represent it in brackets because this is not amplitude, this is a strength or area of this impulse, because amplitude is infinite, undefined. We cannot say it in terms of that. Okay, so this is how a unit impulse function looks like. Now, if I ask you to find convolution between some xt and delta t, what would you do? You would say this is same as writing x tau delta t minus tau d tau. Now we know that everywhere outside t not equal to tau, right? Means if everywhere where t is not equal to tau, this function is equal to 0. Right? That means obviously everywhere where t is not equal to tau, the product of these two functions is also going to be 0. Means the only point where the product of these two functions is not going to be 0 is at t equal to tau. At t equal to tau, you can consider this to be a constant value, xt, right? So only at tau equal to t do you have the product as non-zero. So I could simply take it outside for that moment and do an integration of minus infinity to plus infinity delta t minus tau d tau, and we already know by definition, no matter where this delta is situated, this area is equal to 1, which means this gives nothing but xt. That means if you find a convolution of xt with a delta function, you get the same function back. Now what would have happened if this was not delta t, this was a delta t minus capital T? You would have written the same thing, right? And instead now, just to make things simpler, you could have written, using commutative property, you could have written x of t minus tau delta tau minus t d tau, meaning first write both in terms of tau, and if you choose to flip and shift x tau, you could have written that this is x of t minus tau delta tau minus t d tau. Now obviously this function is 0 everywhere else other than tau equal to t, right? So this product will be non-zero only at capital T, and that means I could have just taken this x, plugging in tau equal to capital T, I could have just taken this out, because at that infinitesimally small value of tau, this is like a constant, and I could have said this, and we know that this is equal to 1. That means you get t minus t. So if you perform a convolution of xt with an impulse situated somewhere, what you're basically doing is moving that signal to the location of that impulse. So xt now moves to xt minus capital T. So obviously in this signal, what is going to happen? If this is xt and you find an impulse, find the convolution with an impulse situated at t equal to 2, what is going to happen? You are going to eventually land at x of t minus 2. So this whole signal moved to the right side by 2 units. That means minus 1 moved to 1, 3 moved to 5. This is how yt, which is the convolution of xt and ht, look like. Okay. Always remember that only that whenever you have a signal and you find a product of this signal with a delta function, the resultant will always be a delta function. Okay. But if this was under an integration, if this delta function was being multiplied with some signal under integration, then you get rid of that delta function. Okay, that's the only way to get rid of a delta function. Otherwise, you cannot get rid of a delta function. If you find product of delta with some other function, you output is always going to be a delta function in terms of a delta function. Okay. Here, because this was convolution and there was integration, we got rid of delta. Okay, moving to question 6. So question 6 basically asks us to determine and sketch the responses of a linear time invariant system with an impulse response ht. Now in this particular question, we have a system which is known to be LTI, And this time, the impulse response of this system, HT, is known, right? And what the question asks us to do is that it gives us two signals, x1t and x2t, and asks us to find the output for each of them. So we're going to start with x1t. What is given is that HT is e to the power minus t by 2 ut. Okay, so you also already know that to find the output of any LTI system, all you've got to do is find the convolution of the input with its impulse response, right? And doing convolution graphically is always very, very easy, and it helps you avoid make mistakes if you draw the flipped and shifted version correctly. So let's see. Now let us see how this HT looks like. HT is a decaying exponential, right? And ideally, how would this e to the power minus t by 2 look like? It will be something like this. So as t tends to infinity, it tends to 0, and at t equal to 0, its value would be 1, right? But because you have ut multiplied with it, ut is a unit step function, right? Unit step function is something like this. Its value is 1 only for t greater than 0, right? So the moment you multiply that with any function, you're basically getting rid of all the values to the negative side of t. All right, so this is your ht, right? And what is the first step we do towards finding convolution? We write it in tau domain. So I'm just going to change this and make it h tau, right? And what is this function? In terms of tau, it is e to the power minus tau by 2. All right. Now, what else is given? x1t is given. x1t is given to be a signal like this. Okay, this is one of the inputs. So obviously between the two, the easier one to flip and shift seems to be x1t. So this is what I'm going to go with for flipping and shifting. So first step, converting this to tau domain. So I'm going to write it as x of tau. This also becomes tau. Okay. If this is x of tau, then what is x of minus tau? Remember what I want eventually? I want x of t minus tau, because to find convolution, I am looking to find this expression, integration minus infinity to plus infinity x. Now I've decided to flip x tau, right? So I'm going to write xt minus tau h tau d tau. This is what we need to compute. So h tau we already have here, right? I need x t minus tau. That's what I'm trying to obtain. So if this is x tau, what is x of minus tau? This is x of minus tau. X of minus tau is like saying x of 0 minus tau. So if I was to write it in terms of t minus tau, this is the particular case for t equal to 0. Now we notice that for t equal to 0, this edge is at location 0, right? Which means that in general, if this was at any t, then this function would have been x t minus tau, right? So it's very important that we take care of the extremities, and with that we have arrived at the function x t minus tau. Its value is 1. Okay, for less than t its value is 1, for greater than t its value is 0. So this is what is x of t minus tau. Now I have both the signals with me, and now all I have to do is find the product, right? But depending on what is the value of t, this product may vary, right? So I have to find yt, this y1t, the convolution for all t, correct? So now we are going to take different cases and write the convolution. Okay, so the first case, your x of t minus tau is suppose somewhere here. So this is t, right? So this is the case when there has been, t is less than 0. So there is still no overlap between xt minus tau and h tau. So if I was to write for t less than 0, this leading edge of xt minus tau hasn't really reached here. In that case, we can clearly see that yt, this product, is equal to 0, right? Next case, let us say it has entered. Okay, so there is an overlap, right? And now, of course, the convolution will not be 0, and the case here would be for t greater than 0. Now, what can we write? Yt would be this product. What are the limits now? We notice that this is the only area of overlap. So we will write 0 to t, the two functions. What is h tau here? H tau is e to the power minus tau by 2. And what is x t minus tau? Its value is 1, d tau. So you compute this value and you would get e to the power minus tau by 2 d tau. Integration of this is e to the power minus tau by 2 divided by minus half, right? So you get a 2 here with a minus sign. Here you also need to put limits from 0 to t, and when you do that, you would get minus 2 e to the power minus t by 2 minus of e to the power 0, and this would give you 2 minus 2 e to the power minus t by 2, or 2 minus e to the power minus t by 2, right? So this is the solution, and let me summarize it. Now there is no other case, right? Because there is no other trailing edge of this signal, the signal xt minus tau. So these are the only two cases. T can go on increasing in this direction, but this signal will not change. Like the limits will not change, or overlap will not change. Overlap will remain from 0 to t. So this is it. So we can write yt as 0 for t less than 0, and 2 1 minus e to the power minus t by 2 for t greater than 0. So this is what is y1t, okay, when input was x1t. Okay, this is all x1. Okay. Now moving to second part, x2t is given to be a signal like this. Okay. So this is x2t, and now we need to find convolution of this with the impulse response ht, and this is what should give us y2t. Okay, so the system is the same. Now again, x2t is much easier to reflect and shift. So what I'm going to do is obtain xt minus tau, right? That is my task. x2t minus tau. This is what we need to obtain. Here I'm just going to make it quickly, everything in terms of tau. Now if this is x, and this also I'll make it in terms of tau. So x2 tau. Right? If this is x2 tau, what is x2 minus tau? This is x2 minus tau. If this is x2 minus tau, this is a special case where t is equal to 0. That means if I was to now shift this whole block by an amount t, right? As if this edge, this leading edge of this pulse, this is at 0. So if I had to move this whole thing by an amount t, that means this 0 will actually now go to t, and this 3 will now go to t minus 3. Okay, that means my x to t minus tau looks like something like this. So t minus 3. It's very important, and I'm insisting this again and again, that you establish these limits correctly, because if you make a mistake at this point, your entire solution will be wrong. Okay, because you'll be plugging in wrong limits everywhere. So So now that we have both our actors ready, let us start finding the convolution. So as the practice goes, the first case, which is like this, if this is the case, and what does this case look like? So this leading edge has not yet reached 0. That means for t less than 0. You notice there's no overlap and yt is equal to 0. What could be the next case? It's moving closer, and the case is something like this. I'm not drawing it to scale because obviously this value is 1. So let me actually redraw it if you want it to be in proper scales. So let this be e to the power minus tau by 2. And now you have a signal whose leading edge has entered, right? But the trailing edge hasn't. Something like this, right? So what is the region of overlap? This is the region of overlap, and this is the only region of overlap. Everywhere else the product is 0. So if I was to write the convolution, how do I write? And what is the condition here? That for t greater than 0, but t minus 3 is still less than 0, right? So t is greater than 0, but t is still less than 3. That means t is between 0 and 3. So for t between 0 and 3, how do I write yt? Integration from 0 to t, okay? And the two signals, so the first signal h tau is e to the power minus tau by 2, and what is the second signal here? Its value is 2 d tau. So 2 e to the power minus tau by 2 d tau is what you need to integrate, and when you do that, what will you get? You will get 2 e to the power minus tau by 2 divided by minus half limits 0 to t. So this becomes minus 4 times e to the power minus tau by 2, and when you plug in these limits, you will get 4 times 1 minus e to the power minus t by 2. Okay. What is the next case? Next case is that xt by 2 has further progressed, and now this time even the trailing edge has entered the zone, so it is t minus 3. Now what is the overlapping area? You notice that this is the overlapping area, right? Only in this, from t minus 3 to t, this is the only area where there is an actual overlap between the two signals. Everywhere else this product is going to be 0. Okay, so now how do I write this condition? Now the condition is that for t minus 3 also greater than 0, that means t greater than 3, right? And how do we write yt? This time, now the signals remains the same, right? So this is 2, so this is still e to the power minus tau by 2, and this is still 2 d tau, but the limits now are between minus t minus 3 to t. This is what makes all the difference in your solution, and you'll find that the same signal, minus 4 e to the power minus tau by 2, now you've got to put limits from minus t minus 3 to t, and when you do that, you will end up minus 4 e to the power minus t by 2 minus e to the power minus t minus 3 by 2. Rearrange it a little bit. Take e to the power minus t by 2 out. So, and I'm going to flip the sign. So 4 e to the power minus t by 2, I'm taking it outside, and this then becomes, so this is what? E to the power minus t by 2 plus e to the power 3 by 2. Right? So this becomes e to the power 3 by 2 minus 1. Right? And is there any other case left? No. Now that this xt minus tau, x2t minus tau, it can go on moving, there will be no change in limits. The overlap will always be between t minus 3 and t. Right? So how do I summarize the solution? y2t is 0 for t less than 0. Its value is 4 1 minus e to the power minus t by 2 for t between 0 and 3, and its value is 4 e to the power minus t by 2 e to the power 3 by 2 minus 1 for t greater than. So this is your answer. Okay. Question also asked, and I forgot to do that. Question also asked us to sketch the solution. So let us sketch the first one first. This one first. This was for y1t. How does this signal look like? You notice that this is a decaying exponential. So one thing is clear, that we don't have to worry about what is happening for t less than 0, right? Its value is 0 only. But what about after t equal to 0? 2 into 1 minus t minus 2. So this is 2 minus 2 e to the power minus t by 2. So how does e to the power minus 2 look like? E to the power minus 2 looks like this. And if you multiply it with 2, that means at t equal to 0, its value should be here, right? Now, there is a minus sign in front of it. That means you'll have to reflect it. That means this is how minus 2 e to the power minus t by 2 looks like. And now you add 2 to it, to the whole signal. That means this whole signal will move up by 2 units. That means whatever was at minus 2 now comes at 0. Right? So how does your final signal look like? The final signal looks like this. Okay? And asymptotic, it's going towards 2. This is how y1t looks like. Okay? Now let us see how y2t looks like. This is how the signal would look like. Now part B of this question asks us to verify y2t in terms of y1t by using the property of LTI system. That means we can clearly see that if we look at x2t, x2t is a signal like this. Right? This is what was x2t. And what was x1t? This was x1t. Right? So if I asked you to write x2t in terms of x1t, what would you have to do? You would have to first multiply x1t with the 2. Okay, so this becomes 2 now. Right? Now, if you shifted this 2x1t to the right and brought in a signal like this. Okay, so this is what? 2x1 t minus 3. And now if you flipped it, that means you multiplied it with a minus sign, this. Okay, this is what? Minus 2x1 t minus 3. So you've got two signals, 2xt and minus 2x1 t minus 3. If you add these two up, what would you get? You would get nothing but the same signal that you were looking for, right? x2t. That means that x2t can be written as x1t, sorry, twice of x1t minus x1t minus 3. And because this is an LTI system, if x1t fed into an LTI system gives y1t, then twice of x1t minus x1t minus 3. If this is fed into the same system, what should it give? Because it's an LTI system, it should give twice of y1t minus y1t minus 3. Right? We already know what is y1. So this part B of this question asks us to verify whether this is actually same as what we got here. Okay? If this y2t is same as 2y1t minus y1t minus 3. So we already know what is y1t. Let's check it. This is y1t, right? Okay, so we are trying to find out the value of 2y1t minus y1t minus 3, right? So it's obvious that if you look at yt minus 3, it has no value or no effect on y1 when t is less than 3, right? That means we can easily say that between t equal to 0 and 3, okay, and let me put an equality here. In this region from 0 to 3, yt minus 3 has not even featured yet, because it is y1 t minus 3 is the signal that you get after shifting y1 by 3 units, right? So in this interval, this function is nothing but 2y1t. And what is this function that we're trying to write? It should have been equal to y2t, right? So in this range for t between 0 and 3, y2t should be nothing but 2y1t. And what is y1t in this interval? y1t for t greater than 3 is 2 1 minus e to the power minus 3 by 2. So this becomes 2 times 2 1 minus e to the power minus t by 2, that is 4 times e to the power minus t by 2. Okay, case 1. Next, for t greater than 3. For t greater than 3 is when this signal has also come into picture, right? And in that case, we can say that y2t would be what? Now y2t can be written as 2 times y1t minus y1t minus 3. So you'll get 4 1 minus e to the power minus t by 2 minus 2 times yt minus 3. So 4 times 1 minus e to the power minus t minus 3 by 2. Okay, just plugged in t equal to t minus 3 in the same expression y1. So if you simplify this, you will get 4 e to the power minus t by 2. If you take it out common, and you will be left with e to the power 3 by 2 minus 1. Okay, and not to mention that the other case for t less than 0, both are already 0, right? So you will get y2t as 0. So let us check. This is actually what we got by finding the convolution also. So for t less than 0, let's cross check. Right, so we have to check between these two. So for t less than 0, it was 0, correct? For t between 0 and 3, it was 4 e to the power minus t by 2, correct? And for t greater than equal to 3, it was this value. So this is what should have been, and this is what is, right? So this is what the question asked us to prove for an LTI system.